Hello and welcome. My name is Florin Bobaru. I'm a professor of mechanical and materials engineering at the University of Nebraska-Lincoln. And it is a great pleasure to introduce today Dr. Stewart Silling, distinguished member of the technical staff at Sandia National Labs. Dr. Silling obtained his PhD in applied mechanics from California Institute of Technology in 1986 under the direction of James Knowles. He has been a faculty member in the Division of Engineering at Brown University prior to joining Sandia National Labs. In 2015, he was awarded the Belichko Medal by our association, US Association for Computational Mechanics, for his pioneering work on peridynamics. This work was started 20 years ago while he was on sabbatical from Sandia at Caltech. During that year, Dr. Silling worked on what was to become a landmark paper which appeared in 2000 in JMPS. His next few papers, in 2005 on a mesh-free numerical implementation of peridynamic models, well suited for simulating fracture and failure, and in brittle materials and rubbery membranes. And in 2007 on a vast generalization of theory, the state-based models, have now become classics. These early papers on peridynamics started something. There are now hundreds of papers published each year on peridynamics-related topics. There is a new journal of peridynamics and non-local modeling edited by Dr. Silling and Professor Erdoğan Madenci from University of Arizona. And many symposia and workshops have been organized at this conference and throughout the world at other conferences over the past decade or so. The global reach of peridynamics can be seen from the research work done in universities ranging from Lapland near the Arctic Circle to New Zealand and everywhere in between, including a large number of research groups at top universities in China, as well as in Italy, Germany, and the UK. Outside the academic and national labs, peridynamics has gotten attention from Boeing, ExxonMobil, Corning, GE, and a discontinuous Galerkin implementation of peridynamics has appeared recently in LS-DYNA. In today's presentation, Dr. Silling will discuss the state of peridynamics today, 20 years after its introduction, and also perhaps offer some guidance on what lies ahead for the next 20 years. Please welcome Dr. Stewart Silling.
Thank you, Florin. Florin keeps trying to put the blame on me for peridynamics, but the truth is he was there almost from the very beginning, as has been a large community of researchers that is now worldwide. Thank you all for attending. This is a great honor and pleasure to be here. In this talk, I would like to explain what the peridynamic theory is for those who might not have seen it before. And I'd like to offer some personal recollections and reflections on the evolution of the theory over the past 2 decades and some thoughts on where things stand and future work. First, I will try to explain what the theory is for and what it seeks to accomplish. The main thing it was intended for was the modeling of fracture. So I will try to, I'll try to explain how fracture modeling works in peridynamics and where things stand with respect to that major objective. And then I'll talk about other things that people over the years have discovered peridynamics is useful for. So I hope that by the end of this talk, most people will agree that peridynamics is a reasonable theory that doesn't violate any laws of physics or mathematics at least, and is useful for some applications. To motivate what peridynamics is, consider the problem of understanding what goes on in the process zone near a crack tip. It is widely believed that what goes on in that process zone is kind of the culmination of many interacting physical processes, some of which involve the nucleation and initiation of pre-existing defects. But somehow, the mystery is that a point starts out where the deformation is continuous, and somehow it ends up at a point of discontinuity, in other words, on a crack surface. So how to model that within a continuum mechanics theory is, to me, a deep mathematical mystery, and that is something that peridynamics may be able to help understand. So the ideal mathematical tool for simulating this problem would be a theory which seamlessly transitions from continuous to discontinuous deformations, reflecting the process I just described, where a point starts out in a continuous part of the deformation and ends up on a crack surface. So to understand the point of departure of peridynamics from traditional approaches, what I've listed here are some peridynamic answers to some simple questions about how to model fracture. So the first is, why is fracture different from other kinds of deformation? And the peridynamic answer to that question is, it isn't. It's all the same. So why are special techniques needed to model fracture? The peridynamic view is they're not. Why does everybody think they are? Because nearly everybody is used to applying a theory of continuum mechanics that relies on PDEs. The problem being that in order to make a PDE work, you need to be able to evaluate the partial derivatives of the deformation everywhere. So of course this assumption breaks down on a crack where the deformation is singular. So how can we avoid this problem mathematically? What might work better? And the peridynamic view is integral equations might work better, and that's what we're going to try to use. The momentum balance in peridynamics is an integral equation that sums up force interactions along what are called bonds, characterizing the force density exerted on any point x by its neighbors q within some cutoff distance for these force interactions. That cutoff distance is called the horizon, which may be viewed as a material property. So this is a different mathematical picture from the standard Cauchy PDE, which would have this term for the internal force interactions replaced by the divergence of a stress tensor field. The stress tensor is basically not used in peridynamics because that is where all the partial derivatives live that we want to omit. If this force density obeys this symmetry or anti-symmetry, then Newton's laws are automatically satisfied. Linear momentum is conserved. Angular momentum conservation is guaranteed by additional requirements on the material model. Now, what a material model does in peridynamics is it evaluates this function F representing the bond forces. Since this is a numerically oriented conference, I will jump ahead to the simplest numerical discretization, which involves simply replacing this integral by a finite sum. The sum is over nodes that are defined to have a definite mass and volume in the reference configuration. So some good features about this discretization, which is really kind of the workhorse that most people in the community use, are first of all that it's simple to program. Another is that it conserves linear and angular momentum exactly, provided the underlying material models do the same. In fact, this discretization itself, if you think of it as a body in which the points are, in which the mass is distributed on delta functions, you can think of this discretization itself as being a peridynamic body. So what's interesting about that is any result about the continuum model automatically applies to this discretization. And that's not true of all possible discretizations of the peridynamic equations. Some disadvantages of this discretization that people have discovered over the years is, for one thing, it produces what's sometimes called peridynamic dust, meaning that as damage accumulates, nodes tend to fly off and become completely detached. Another is there are some little convergence issues that occur. If you consider the convergence as the horizon approaches zero, if you change the discretization so that a constant mesh spacing exists through the number, the ratio of the grid spacing to the horizon is constant, then it's been proven by Professor Dew at Columbia and his team that this discretization converges, but sometimes it converges to the wrong thing. So that's called asymptotic incompatibility. The simplest material model in peridynamics is called microelastic. And what that means is each bond responds independently of all the others within the same family. So in a linear microelastic material model, the model is just a graph of bond force versus bond extension. In other words, elongation of the bond. And in a linear microelastic material, this is a straight line. However, the force density vector in the bond rotates along with the bond as the bond deforms. So in a sense, you get geometrical nonlinearity for free in spite of this apparently linear behavior. So this is useful in modeling all kinds of problems such as buckling. To model damage, one thing we can do is apply a bond breakage criterion, meaning that when the bond extends too far, it breaks irreversibly, after which it no longer sustains any load. And just using this simple concept of damage, you can simulate all kinds of interesting things with this meshless discretization, such as Hertzian cracking in a brittle material, and also erosion by impact of particles on a brittle target. Fracture occurs spontaneously or autonomously, meaning that nobody is telling cracks what to do. When one bond breaks, its neighbors are more likely to break, leading to a process of progressive failure. So peridynamics has proven to be useful in simulating problems like fragmentation, where there's a need to simulate many mutually interacting cracks that can grow in any direction. Crack stability, similarly, is reflected in this autonomous crack growth idea. So this is, these are simulations of a brittle plate with a center crack in biaxial tension. So we're pulling both vertically, which starts the crack growth, and also horizontally. And if the horizontal stress is sufficient, it becomes energetically favorable for the crack to turn. And this is a form of crack instability because it can grow either one direction or the other, resulting in these S-shaped looking crack trajectories that are reflected in the simulation. Now, historically, it would have been nice to spend 5 or 10 years establishing the fundamentals of the peridynamic method in simulating simple problems in fracture mechanics. The reality didn't work out that way. So peridynamics got started in approximately the year 2000. After 2001, after the 9/11 attacks, there arose a need to analyze the possible impact of airplanes onto nuclear reactor containments, which are big, heavy, reinforced concrete structures that are designed to keep radioactive contaminants inside the building if a nuclear reactor accident occurs. So when a situation like this arises, if you work at a national laboratory and if you're fundamentally an engineer, as I am, you can't just say, sorry, my method isn't good enough yet, come back in 5 or 10 years when it's perfect. You have to use the tools that are available at the time. So that's what we did with peridynamics. This is a simulation of an actual experiment they did where they crashed an F-4 fighter plane into a very big, heavy, reinforced concrete target. Professor Gerstle at the University of New Mexico has developed a fast-running peridynamic code that he uses for modeling all kinds of problems involving reinforced concrete, and he wrote a book about this method shown here. So what have we learned about damage laws in peridynamics? I already talked about the simplest brittle microelastic material model. One problem with that model is that for a given value of horizon, the peak load, which is determined by the maximum in this bond force curve, depends on the predicted value of G1C, the critical energy release rate. But by putting a tail on that material model, you can alter the area under this triangle, allowing you to independently determine both the maximum stress that the material can sustain as well as the critical energy release rate. You can also implement bond failure criteria that respond to rotation angle between bonds, in other words, shear, allowing you to independently specify G2C as well as G1C. And you can do fancier things like develop a nonlinear or non-local damage mechanics approach to failure of bonds. Professor Bobaru and others have studied pretty carefully the properties of the peridynamic method in simulating dynamic fracture in brittle plates. So these are some of their results showing convergence in a rather subtle problem, which is crack branching in a glass plate. And their results also show approximately the right asymptotic crack growth velocity, which is related to the Rayleigh wave speed in a brittle material. So that's sort of a success story. People have looked at a lot of other possible uses of peridynamics in simulating fracture. For example, there's a need in the movie industry for computer methods to animate fracture, make movies involving fragmentation and fracture. So these are from a paper that appeared several years ago in the computer animation community. This guy is called a Welsh dragon, which is apparently something that people like to model in that community. I don't really know whether peridynamics is fast enough to become very popular in that community, but still it's interesting that it gives these nice results. One feature that you get for free with peridynamic modeling of damage is you accumulate these broken bonds over time. So this is a simulation in which we hit the edge of this brittle plate with a hammer many times. And each time you hit it, the damage that was already there grows farther, plus you introduce new damage. And eventually the hammer breaks through, and you can see some of this so-called peridynamic dust that is created in this meshless discretization. Fragmentation is another natural application of this method because you can simulate a lot of mutually interacting cracks without having to specify the growth of each one according to some external criterion. Other applications include thermally driven cracks, such as this interesting pattern that is obtained in glass, in which there is a temperature gradient from left to right. And this is a simulation that some researchers at Corning did, studying the residual thermal stresses in glass. Now, at the beginning, I referred to this mysterious process by which cracks appear and grow. So what we've learned a lot about in the past 20 years regarding crack nucleation is that in peridynamics, it can be viewed as a type of material instability in which when bonds start exceeding the maximum in their force versus extension relation, in effect, the wave speeds become imaginary, resulting in a type of material instability that results in the nucleation of a crack. And this same instability exists as the crack grows ahead of the crack tip. Anisotropy can be modeled by allowing the bond properties to vary with direction. So in a lamina, in a unidirectionally reinforced composite, you can have bonds that are parallel to the fibers, much stiffer and stronger than all the other fibers. You can also have the bond properties vary continuously according to this, to some function like this spherical harmonic pattern that's shown here. So just using these concepts of anisotropy, you can reproduce a lot of realistic features of damage and fracture in composite laminates that are used in the aerospace industry. Dr. Patrick Deal at Louisiana State University has done a great service to the Peridynamics community by compiling in a review article in the Journal of Peridynamics and Non-Local Modeling many of the validation studies that have been done over the past 2 decades. The first issue of this new journal appeared earlier this year, and we hope that someday it will become the first choice for people working in the peridynamics and non-local modeling communities. Now, why should you publish in this journal rather than a more established journal? Well, for one thing, I think most of us in the peridynamics community have experienced getting reviews after 6 months, and the reviews say, "I've never heard of peridynamics. What is it? I can't accept your paper." So I anticipate that if you submit papers to this journal, you won't get reviews like that. There have been a few books that have been written. I already mentioned Walter Gerstel's there's a handbook of peridynamic modeling, Medenci Anotarchus's book, and a couple of others. In 2007, in response to the lack of generality of bond-based materials like the microelastic material I talked about before, we started working on state-based material modeling, which is a more general version. The problem with assuming that each bond responds independently of all the others is that it results in some restrictions on the material properties you can reproduce. Notably, you always get a Poisson ratio of 1/4. So to avoid that, we developed a more general framework for material modeling called state-based rather than bond-based. And the idea is that the bond forces are determined not only by the deformation of the individual bond, but also collectively by the deformation of the entire family. So using that generalization, you can simulate interesting things like fluid fracture, so to speak, as well as fluid structure coupling. Now this funny-looking notation is state notation, and these are non-local operators that allow you to manipulate these families of bonds and functions of those families of bonds in a compact form. I won't have time to go into the details, but using this type of notation, in spite of the complexity of determining the dependence of bond forces on the totality of deformation of their family, you can precisely specify everywhere in a body what the bond force is in terms of the deformation. As an example of the power of state-based material modeling, this is one possible way of modeling plates and shells as state-based peridynamic materials. The idea is that the material model resists relative rotation between bonds that are in the same family. In other words, it resists bending. And that notion of modeling plates and shells can be combined with appropriate damage modeling for those kind of structures, resulting in realistic looking failure patterns. The most widely used state-based material model is called correspondence materials. And in those materials, a conventional stress-strain relation from the standard theory is used as an intermediate step in determining the bond forces. So that's a great convenience because you can recycle all your favorite material models from a finite element code. The problem is there are a lot of practical issues like zero energy mode instabilities that arise, but many people have looked at that problem, and there are a number of proposed ways of mitigating those, and all these methods seem to work pretty well. So correspondence materials are kind of the workhorse for modeling ductile failure in peridynamics. And most of the time they work pretty well. Because peridynamics is a non-local theory, there is the possibility of using it more effectively than the standard theory as a way to coarse grain atomistics and to implement atomistic to continuum coupling. And there have been some studies of that, but it seems to me there's a lot more that could be done in the future. Interestingly, you can go directly from statistical mechanics to a peridynamic continuum model, and that result was explored by LeHoucq and Sears in about 2010. One of the things we've learned a lot about over the past 20 years is the relation of peridynamics to the Cauchy theory. You might expect that as we reduce the horizon to zero, we should in some sense recover the standard PDEs. And that's exactly what happens provided the deformation is continuous. Interestingly, if you have a non-convex elastic peridynamic material, meaning the bond forces go up and then down, the limiting case as you reduce the horizon to zero is you get Griffith cracks. In other words, jump discontinuities in the deformation that consume a definite amount of energy per unit surface area as they grow. And then you get the PDEs away from this jump discontinuity. So that's a very interesting result that Professor Lipton at LSU and his team have explored. There continue to be some usability issues with peridynamics, especially with this meshless discretization that a lot of people use. Boundary conditions are different than people are used to with PDEs. The material properties of nodes are affected by how close they are to a free surface. That's sometimes called the surface effect in peridynamics. You also tend to get this dust phenomenon that I mentioned. So even though there are a lot of proposed fixes for this, I think what would be a good thing to do is have a committed team of software-oriented people who are willing to dedicate themselves to making Peridynamics look more like the standard finite element tools that typical engineers are accustomed to using. Because Peridynamics is a non-local theory, linear waves are dispersive, and that's both good news and bad news, as we've learned. It's good news because real materials are dispersive, at least at small enough length scales. But it can also, so this provides an opportunity to fit measured dispersion data from ultrasonics or other techniques to a peridynamic material model that would reproduce it. However, dispersion can also be kind of a nuisance in macro scale simulations where it can non-physically alter simulations of wave propagation in some applications. Another thing we've learned is that in trying to solve quasi-static problems, the fact that in peridynamics there are so many of these bond interactions for each node, you get matrices that are much more dense than you would in a finite element code. And as far as I know, tools for dealing with these dense matrices or even storing them are a challenge. And as a result, most people continue to use dynamic relaxation, which is reliable, but it has some known limitations. So in conclusion, let me give you my personal impression of where peridynamics is now. And from this map, you can see that one answer to that is it's in a lot of places, as Florin mentioned in the introduction. So I think the basics of the mechanical and even thermodynamic theories, including non-local diffusion, have been worked out. But the sky is the limit in terms of dreaming up new material models to accomplish different things. As I mentioned, a plate and shell theory within peridynamics can be implemented just by choosing the right state-based material model. So this is in contrast to standard plate and shell theories where you have to invent a whole new PDE, a fourth order PDE, which does not follow immediately from the second order PDEs of the standard continuum mechanics theory. And there are other examples of that in which just by choosing a peridynamic material model, you can reproduce phenomena like solitons that in the standard theory would require the development of a whole new PDE. So I've listed my opinion about some promising areas for growth that I foresee in the future, including further development of the connection between peridynamics and atomistics. Now I started out by talking about the fracture process zone as kind of a motivating problem for developing a theory like this. Yet here we are 20 years later, and as far as I know, no one's really seriously applied peridynamics to that particular problem of understanding the process zone. There have been many efforts, and I think there's more work to be done on multi-scale aspects of peridynamics, fluids and fluid structure coupling, complex fluids, because there are non-local interactions, biological type materials, including fluids, solutions of long molecules. Many opportunities for multi-physics, coupling of different physical fields, direct implementation of the peridynamic equations in a finite element solver, implicit and quasi-static solvers, as I mentioned. My personal areas that I'm working on now, my personal favorites are material stability and non-local waves, which are turning out to be a pretty interesting area. And as I discussed, there's a close connection between material stability and crack nucleation and growth in peridynamics. People are starting to look at a true Eulerian formulation rather than Lagrangian. And I think there are lots of opportunities for modeling geological media, poroelasticity, mixture theories, and so on. So I'll stop there. Thank you.